Hello, Honors Algebra 2 and Algebra 2 kids. We are on lesson 5.4 on page 140 of your student journals. And what we're going to be talking about today is a lot about solving. So what you're going to see me do today is kind of work through a whole bunch of examples. And that way, hopefully, we can kind of cover all of our bases when it comes to solving all the different various forms of radical equations. And then you're going to do a lot of practice, some on your own and then some in class as well. All right, so the first thing I want to talk about is this beginning thing. So a radical equation doesn't necessarily just have to have a radical sign. So like, for example, you could have the square root of x minus 1 equals 10, right? And so that would kind of be what you think of as a radical equation. But you can also have the same equation, but written in with an exponent form. So remember, anything that has a root is considered a radical. And so this and this are essentially the same thing. And so even though that doesn't physically have that radical sign, doesn't mean that it's not a radical equation. And so you have to kind of be careful when you're looking at some of these. And, you know, we're going to get into ones where we might have, I don't know, 2x plus 5, and I might raise it to like the 2/3. So what I'm doing here is I'm saying that this is 2x plus 5 raised to the power of 2, but with a root of 3. So the cube root problem. Whereas this one is only raised to the first power, but has a square root. So again, pay attention to not just the radical signs, but also the exponent, so the exponential form of that, so that the bottom, remember, is your root. The other thing I want to talk about is extraneous solutions. So extraneous solutions means solutions that don't work. And a lot of times we come into that, we see that when we have, and we've done this before with like square root functions and so forth, but anytime you have a defined like domain, for example, there's going to be a restriction on some of your answers that, you know, don't make sense. For example, I'll give you an example. If I had the fourth root of x equals -2. So because I'm taking an even root of x, okay, an even root, so I'm looking for groups of 4, right, 4 of the same number. So what number multiplied by itself 4 times would equal -2? Likewise, if I had the square root of x equals -2, there is no such value in which I would be able to find a value for x to make this a true sentence, because any even root has to be positive. So there's no value of x that would make this -2. And so remember, on your graph, remember what a square root function looks like. It looks like that hook, right? So remember, there's a specific part of your graph that's undefined. So even if I did like your basic square root function, this whole part, like any x value, let's say if this is 0, 0, any x value in this region cause my function to be undefined. In other words, it doesn't work. So it would mean that if I plugged in, let's say x is -2, it would produce an extraneous solution. So again, an extraneous solution means that you can actually kind of solve for it algebraically, but graphically and common sense wise, it doesn't make sense. So in this case, you would say, I'd rather you say extraneous solution. Let me make sure I spell that right. Rather than say no solution. And the reason why is just because you're going to see that word quite a bit. All right, so before we get into like graph or solving a whole bunch of these, there's a couple other things I want to go over. And this idea of plus or minus or no plus or minus. So if you remember when we did square root functions, we did a lot with like, you might probably heard your teacher or me say, anytime you square root both sides of an equation, you're going to put a plus or minus, right? Well, we did that with square root because that was the most common. We're going to extend that thinking. And so anytime, so I'm going to say, when you even root both sides of an equation. Okay. When you even root both sides of an equation, that's when you put a plus or minus. So it's not just limited to square roots. It could be fourth roots or sixth roots or 8 roots and so forth. And then the no plus or minus is when you odd root both sides of your equation. So think about why that is true, right? So remember, if I had, let's take the example, the cube root of x equals -8. Remember, you can have a negative answer. Like I can have a value. The cube root of x could be a negative number. And so in this case, what value of x, well, let's change this because that really makes sense. Let's change that to a -2. What value of x would cause this to be a true sentence? And so what we're going to be looking at here is we're going to say, okay, well, the cube root of x, what number can I plug in for x that would make this a true sentence? Well, the answer would be -8. The cube root of -8 is -2. And so you can have odd values for cube root functions, or even 7th root or 7th root and so forth. Remember what the graph of a cube root function looks like, right? So it's that S-shaped graph. So unlike a square root function where there was like a specific area that was undefined, remember what the domain and range are for a cube root function? It's all real numbers, right? So there are no limitations when it comes to values we can plug in for x. The domain was defined here, right? So it's like all real numbers where x is greater than or equal to 0. Well, here it's all real numbers, period. It's all real numbers. So therefore, there are no limitations when it comes to the values that you put in for your x and for your y. All right. So what I want to make sure that is that anytime we even root both sides of an equation, you're going to have two possible answers. Anytime you odd root, you wouldn't. So let me go over two quick examples and I'll show you what that means. So this might be something that we do. This is an example of x to the 4th equals 81, so it's a polynomial. So what we're going to be asking a lot today is kind of what is the inverse or opposite operation. So when you raise something to the 4th power, the inverse is raising something to the 1/4. Or in other words, you're raising or you're taking the 4th root. So I don't really care if you write it as, and I'll show you another way. So if you think of it as the 4th root of x to the 4th, think of it as x to the 4th to the 1/4. Remember, those mean the same thing. Ultimately, what happens is you think about your exponent properties, 4 to the 1/4 will give me 1, right? So remember that whatever you do on one side of your equation, you do on the other. So this is the 4th root. And so either way, you're going to end up with the same answer. So this is an example where because we took a 4th root, we're going to put a plus or minus, and then the 4th root of 81 is 3. Another example would be something like x to the 2/3 equals 16. So x to the 2/3 equals 16. Again, doesn't look like a radical, but it is. So another way of writing that would be the cube root of x squared equals 16. So you could think of it in radical form if that makes it easier for you. I personally don't think it does. Because in here, I have to do a couple different operations in order to solve that. And not that that's a bad thing, but I think that it ends up being more work than what you need to do. All you need to do here is think about this property here where we're talking about how we get this to be x, right? We're trying to get rid of that 4th, so we raised it to the 1/4. And the reason why is because when we multiply 4 times 1/4, it equals 1. Well, what do I raise x to the 2/3 to in order to get this to be 1? The answer is the reciprocal. So 2/3 times 3/2, what will happen is you'll get 6/6, or in other words, x to the 1st power. And so essentially all you're really doing here is you are raising both sides. So again, you think of it as you're raising both sides to the 3rd power, but also taking the square root. So you're raising both sides to the 3rd power, but also taking the square root. So because we took an even root, so again, this is your root. Because we took an even root, we're going to put a plus and minus in front of that. All right, so let's do this one without a calculator. So if I did 16 to the 3/2, remember you would break apart the root and the power. And so what this would become is 16 to the 1/2 is the same thing as saying 4, right? Or the square root of 16. And then I get 4 cubed. So my answer, 4 cubed, is 64. 64. All right, what we're going to focus on now is a whole bunch of solving examples. And so I'm just going to walk through a whole bunch of problems. So I'm going to try to do the odds, or at least several of the odds. And then I'm going to save some for the rest of you. Save some for you to kind of do. All right, so on this one, we have a whole bunch of different types of equations. This one is a radical equation. Same idea as what I did on the other side. You want to think about what's the inverse operation. Your goal is always to isolate your radical. All right, so get everything away from the radical. What I mean by that is, like in number 4, see how there's a 2 in front? You would get rid of that first. Or if there was a 4 in front or whatever. So the inverse operation of a square root would be to square both sides. So the opposite of square rooting is squaring. Remember, we're squaring both sides, so do we need to put a plus or minus? The answer is because we're squaring both sides, not rooting both sides. Yeah. All right, so when the square root square cancel each other out, I get 1 minus x. I get 49 on this side. Remember, the only time you have to put the plus or minus is if you root, an even root, both sides of your equation. I'm going to subtract 1, and then I am going to divide by negative 1. I get negative 48. So what you want to do here is, again, because square root functions tend to have some opportunity for extraneous solutions, you want to check your answer. So does 1 minus negative 48? So 1 minus negative 48 would be positive 49. The square root of 49 is 7. So check your answer by plugging it back in. Once you know that it works, you can call that a solution. Let's try number 3. So notice there's a 6 and a 4th here. So again, kind of like you would in a linear equation, get rid of your constant term, or their 6 first. So let's subtract that. And then let's get rid of that 1/4 by multiplying both sides by 4. So again, all we're doing is isolating our radical. So what is the opposite or inverse of a 4th root? Well, the 4th root, the opposite of a root, is a power. So we're going to raise this to the 4th power. So the inverse of a 4th root is a power. So I get 2x equals, again, I don't need to put plus or minus because I didn't do roots to both sides. I would need a calculator for this one, and I got 65,536. And then, of course, I divide by 2 and get 32,768. And so I would plug in my answer. 2 times this would give me 65,000, and I know that the 4th root of that was 16 because we already did the math here. And then 1/4 time, or the 4th root of 16 is 2. The 4th root of 32. The 4th root of 32 is, oh, hang on, let me double check this. All right, sorry. So we did 2 times x, so we get the 4th root of 65,536, okay? So again, if you want to do that in your calculator, I just want to show you real quick. If I did 65,536, remember to take the 4th root, you could just raise it to the 1/4 power. So you get 16. So the 1/4 of 16 is 4, and 4 plus 6 is 10. So that does work out. So I'll call that good. All right, let's do some others. On number 5, this one's a little bit more challenging. So on number 5, you have to get rid of this radical. It's already isolated, so that's good. But in order to get rid of this radical, you have to square both sides. So be careful here that you're squaring the quantity x minus 7 and not just x and then negative 7. You're not squaring each one individually, you're squaring the entire left side of your equation. So on this side of your equation, you need to remember that you are factoring here, or foiling here. You are expanding that. That is a binomial squared. So it's x minus 7 times x minus 7. And on this side, I would just get x minus 5. And the reason why is because the opposite or the inverse of a square root is a square. All right, I'm going to FOIL this out. And then I'm just going to, it looks like it's quadratic, so I'm going to go ahead and solve it, set it equal to 0. So subtract x, add 5. And then I am going to factor. I would strongly encourage you to factor every single time here. Anytime you get a quadratic, in most cases, it will be factorable. So numbers that multiply to positive 54 but add to negative 15 are negative 6 and negative 9. So my solutions would be x equals 6 and x equals 9. All right, and this is always true, but in a lot of cases where you have 2 solutions, one of them tends to be extraneous. So let's check our answers. If I plug in 6, 6 minus 7 is negative 1. Can the square root of something ever equal a negative? And the answer is no. So this one's extraneous, and I'm just going to put EXT for extraneous. Let's check 9. 9 minus 7 is 2, so this side gives me 2. This is 9 minus 5, which is 4, and the square root of 4 is 2. So 9 works, but 6 does not. All right, let's do, I don't think I need to do a ton of these, but let's do, I'm going to skip number 7. Let's do, maybe we'll go on to number 11. So this kind of brings you up through a few of these, right? So you've done quite a few of these. Let's do number 11, and that is on page 142. All right, so number 11 says solve the equation, check your solutions. All right, so this one's written in a little different format, which is why I wanted to do this one. So this was written with the radical, or without the radical, it's written with the exponent. But the rules are still the same. Get rid of the 1/2. So you're going to multiply both sides by 2. So you get this. And then what we're going to do next is we're going to get rid of that 2/5, or that 5 over 2. So to get rid of that, something that's being raised to the 5th power and taking the square root, I'm going to raise both sides to the 2/5. And the reason why is so that the 5 over 2 and the 2/5 cancel each other out, which is what I want. So remember, what we're doing to both sides of our equation is we're squaring it and we're taking a 5th root. So we're taking an odd root, which means that I don't have to put a plus or minus because it's an odd root. All right, so on this one, I'm just gonna, this gives me x. Let's go ahead and see if we can expand this out by separating the root and the power. So this would give me the 5th root of 32 is 2, and then of course 2 squared is 4. So let's check our answer. If I plugged in 4, if I took the square root of 4, which is 2, and then 2 to the 5th power is 32, and then took half of it, I would get 16. So again, that checks out, so I'm going to call that a true solution. All right, I'm going to do, the next one I'm going to do is an inequality. And so what we're going to do here, we're going to go over number 13. So we are going to solve this the same way that we would solve an equation. So my first step is to get rid of that positive 3. So I'm going to subtract 3 from both sides. Don't forget that if you multiply or divide both sides by a negative, you have to flip your symbol. So that comes into play here. I'm going to divide both sides by -4. When I divide both sides by -4, I flip my symbol, and this becomes 1. All right, so let's get rid of the square root. So I'm going to go ahead and square both sides. Again, no plus or minus because of the fact that I didn't even root both sides of my equation. And so now I am going to add 1 to both sides. I get x is less than or equal to 2. All right, so here's kind of the deal. So this is not your only answer. So because an inequality means all values, right? So it's like a range of values. It's not just one specific value like we did with the equation, right? It was easy to plug this in and see if it works. Well, with a square root function that's an inequality, or any kind of root function that's an inequality, there could be, especially with an root, there could be times in which that values of x would cause this to be undefined. So remember, if I have a square root of something, we call this the radicand. Not that that's terribly important, but so this radicand cannot be negative if you have an even root. So we want to be careful here. Whoops. We want to be careful here that we also, in addition to the fact that x is less than or equal to 2, but we also have to take into consideration that none of the, whatever values of x also have to be limited to, it cannot make this negative. So the first thing I want to do, or the side thing that I want to do, is I want to take whatever's underneath the radical, which in this case is x minus 1, and I want to make sure that is greater than or equal to 0. Because nothing underneath this radical can be negative. So whatever this expression is has to be positive. So we take whatever's underneath the radical and we set it, so we put it greater than or equal to 0. It can equal 0, it just can't be greater, it can't be less than 0. So then if I solve this one, which is a simple problem, I get x is greater than or equal to 1. So what this means, so in addition to this answer, we also have limitations with that lovely radical there, or that lovely inequality. So my final answer means x is less than or equal to 2, greater than or equal to 1. So there's only this small range of values in which the values of x, those are the only values of x that would make this equation, this inequality true. So remember, this is only true for an even root. So an odd root can be negative. So we're not as limited with an odd root. We're only really kind of limited with an even root. So pay attention. Like here, this is a cube root. We wouldn't have as many issues with a cube root. So we can have a negative number underneath the cube root. But if we have a square root or a fourth root or a sixth root, we cannot have a negative number underneath the radical, so we have to then further define that answer. So all you do is take whatever's underneath the radical and put it greater than or equal to 0 to make sure that that stays positive, and that kind of gives you your boundary lines for your problem. All right, so I gave you some examples. We're going to do some more in class, but I gave you some good examples to kind of practice. I would try some of the solving on your own. Come to class with questions. All right, thanks, guys.